We will now learn how we can characterize point processes. So the fundamental way you can characterize point process is by listing all its realizations and the probability of realizations. But that may be expensive, that may be a little expensive to do that. So there are other ways also which can characterize point process, but not with full information. So just as you know that a random variable can be characterized completely if you list down its range of values and their corresponding probabilities. But you can also characterize random variables by using different measures such as different metrics such as mean, variance, and of course they do not completely or uniquely characterize a random variable, but they can give some information about them. Same way, there are other methods which can help us characterize a point process. First one is, which I'm going to talk about, is the first order statistical measure, which is known as intensity measure. So intensity measure is a measure which means it gives the size of some set in a collection. And what is our collection here? Is our collection is set of all subsets of RD. So our point process is an RD, and we make a collection of all subsets in that space. So intensity measure will take one set, any set, and tell you how many points are there on the average in that set. So intensity measure is the mean number of points. So for any set A, we denote intensity measure as lambda A, capital lambda A, and capital lambda A is nothing but expected value of phi A. Recall phi A is nothing but number of points in A. Okay, and the number of random points in A. And then you take expected, you get mean number of points in A. And I can also write in the following way. Phi A, you know, is summation of indicator of xi belongs to A. And this summation is over all points. We go to each point and ask, are you in A? If it says yes, you add it. You will get a total number of points in A. And this is a random variable because phi is a random process. So phi is a random quantity. So xi are also random quantities. And if I take the expectation with respect to phi, what I get is average number of points in A. Recall that this expectation is actually over the probability space or equivalently the distribution of point process. Okay, so if you know the corresponding probability space, you can take for each relation, you can compute this, multiply by the probability of that relation and add it. Or if you know the probability distribution of A, you can just take each configurations and then you compute the probability of that and multiply it with the number of points in that configuration and you sum it over all possible configurations. Let's see one example. Recall the initial example we have seen. There was a point process where it takes two values. One realization has 2 points and the relation has 3 points. First has the probability 1 by 4 and then has the probability 3 by 4. So in that case, if I take any set A, lambda A, my expected value would be 1 by 4 into the number of points in the first measure plus the first relation measure and plus 3 by 4 into the number of points in the second realization measure. And what is the first measure? It is indicator of whether 1 0 belongs to A plus indicator 1 0 0 1 belongs to A, and this one is indicator 0 0 belongs to A plus indicator 1 1 belongs to A plus indicator 2 2 belongs to A. This is the, if you just put those values back, you get the total values of answer. So basically, you look at you are given any set A and you ask if 1 0 belongs to it, 0 1 belongs to it, 0 0 belongs to it, 1 belongs to it, and 2 2 belongs to it. You get all the answers and weigh them in the following manner and you get the average value. So let's see one example. Suppose my A is this ball centered at 1, 1 with radius 1. So the number of measures, mu phi A, number of points for first relation is 2. number of points in the second relation is 2. Okay, or in other words, this is 1, this is 1, this is 0, this is 1, this is 0. So if I put it back, what I get is 1 by 4 plus 1 by 4 plus 3 by 4, and I get 5 by 4. So this is the average number of points in this ball. I can do this calculation for any set A, and I get the intensity measure for every any set I want. One thing I would like to clarify here, from the notation point of view, is this particular notation. So what I want to say is that this one, both are actually total number of points in set A. Here what I'm doing is I'm going to each point in phi and asking it, are you in A? And if it says yes, I will add 1, otherwise I'll add 0, and I add it. So I get a total number of points in a set A. So this is the point you can look at. There are different points. I go to each of the point and ask, are you in A? And only these points answer 1. So if I add them, I get total number of points in set A. Another way to do this same calculation is that instead of going to each point, I can divide the space into small intervals. And for each interval, I count how many points are there. Okay, and I only count for set A. So I divide the complete space into small interval. Now I look at all the intervals or all the small subsets in A, and for each point, suppose this interval is dx, and I ask how many points are there. So I call it phi dx. Okay, recall dx is a set, and phi dx is a number of points in that set. Okay, recall that phi A is the number of points in set A. So if set is dx, phi dx is total number of points in that set, and here there are 0 points. And this, if I go, the phi dx will be 1. In this case, phi dx will be 2. I take all these small intervals in A, add them all, and I also get a total number of points in set A. So this is, and as I take this goes to 0, this addition converts to integration. So what I get is I go to each subset, and I only look at the sets where that belongs to A. So all the intervals which are outside will be cancelled. So I can do this integration over A, or I can take the integration RD and all have this indicator here, so that whenever you take intervals outside A, you get 0. So those intervals doesn't count. So you are adding over all the intervals in A, and then what you are adding is phi dx, total number of points in the set dx. Okay, and if you add that, you get phi A, and this is also phi A. So just look at this notation that both mean same thing, and the reason we are having these two notation is some places you will see one notation may be giving more information or more or it can help you in equation solving, one of them. So both are same, just remember that. And then once we have this intensity measure, we can define a density. Okay, so point process is said to have a density lambda x if for every set A, you can say the capital lambda A, or the measure intensity measure of that set A, is the integration of this density on set A. Okay, so if you can find one lambda x, again look at this. This is a function of the location. So every location can have different density, and if you integrate that density over set A, you should get the total number of points on the average in set A. Okay, so density kinds of gives what is the average number of points per unit area in a small interval. So how can we compute that? Let lambda x equal to lambda norm of x, and then suppose someone asks you what is the expected number of points in the ball 0R. So to do that, what I do is, if it's a two-dimensional point process, I have to compute this total number of points, average points in B0R, and because this is density, this will be equal to integration over the set A B0R of the density lambda x dx. Now recall this is a two-dimensional integration, so First, I'll put lambda x equal to lambda into mod x. Here, lambda is a constant, and I have to integrate it. It's a two-dimensional integration, so I can use the polar coordinates. In that case, norm x is r, and dx becomes r dr. Then you have to integrate over 0 to pi and 0 to r. This becomes 2 pi lambda r squared dr integration from 0 to r, which becomes pi lambda r cubed. So the true number of points in the ball 0, r is this one. Now, let me also make this distinction between uniform and non-uniform point processes. A uniform or homogeneous point process is the one which has a constant density over the complete space. So recall that the density and the intensity measure are related to each other as the following way. For any set A, lambda A is equal to integration of density over the set A. If lambda x is constant, then it is just lambda. So this will be integration of lambda dx A, and lambda can come out. So integration of dx over A is just the size of A. So what I get is lambda is equal to lambda into size of A. So if for homogeneous point process, the intensity measure is just proportional to the volume of the set. It's lambda into A. So if I have to compute density also, I can just take any set A, compute intensity measure, divide by the size of A, and I get the density. This is true for uniform cases. Non-homogeneous point process or the non-uniform point process are the one which does not have constant density. Right? For example, this particular case, this is a function of x, so it is not a uniform point process. Now take this example, consider two-dimensional point processes, and what you get is, remember, point is this. Now know that this is specific to two-dimensional processes. If you take three-dimensional process, this integration will change, so you get a different result. And in fact, if you are given the same density in, say, it's the same intensity measure in three-dimensional, it will actually be a uniform point process, right? To confirm that, let's take a three-dimensional point process with density 3 by 4 lambda. So in that case, if it's a uniform point process, so if I have to compute this, I will just take the volume of the ball and multiply it by the density. So what I get is 3 by 4 lambda into volume of ball, which is 4 by 3 lambda, 4 by 3 pi r cube, and you multiply it, you get pi lambda r cube. So the same intensity measure of ball 0r, it is in three dimensions a uniform point process. In a two dimension, it is a it's a non-uniform point process. Okay, but the density, of course, would be different. Density is 3 by 4 lambda. In this case, it's lambda x, which is very clear to see that it is non-uniform. You just always note the dimension on you're working on, and you will get different results depending on your dimensions. The way to characterize a point process is by using a finite dimensional distribution, and by this way you can completely characterize or uniquely characterize a point process. So how is it defined? It is similar to the finite dimensional distribution for random process. Let us take n different sets, a1, a2, a3, en, and if we tell what is the probability that first set has k1 points, second set has k2 points, and so on, so that we can write as probability that phi a1, which is the number of points in a1, is k1, number of points in a2 is k2, number of points in a3 is k3, up to number of points an is equal to kn. If I tell this for every value of k1, k2, kn, I am specifying the distribution of this, and that will be a function of a1, a2, an, and k1, k2, kn. And if I specify it for every possible sets and every possible values of n, then I would say that this is the complete finite dimensional distribution of point process. So you can see you would require many values, or it's a very large characterization, because you have to tell it for every possible values of n and every possible sets collection of sets, what is the value that it has any number of points in it. And if I can tell that, then I am uniquely satisfying uniquely characterizing the point process. We will now see some examples of point processes. First is one-dimensional uniform Poisson point process. So a point process phi is Poisson point process with density lambda. So it's a uniform, I'm defining the uniform Poisson point process. So density is a constant. So a point process is a Poisson point process with density lambda if it satisfies the following two properties. First one is, if you take any set A comma B, it's an open interval from A to B, then the number of points in this set is Poisson distributed with mean lambda into B minus A. B minus A is the size of this set. So basically number of points should be equal to lambda into the size of the set. And recall that you know that if there is a site A comma B, then the mean number of points in this set should be equal to density into size, right? Recall the expectation measure. Expectation measure of any set is density into the size of the set for uniform point processes. It's a uniform one. So the mean number of points, any case for any point process should be equal to lambda into B minus A. What is extra here is, because it's a Poisson point process, this number of points, not only its mean should be lambda B minus A, it should be Poisson distributed also. So what is Poisson distribution? This is the form it should take, that probability that number of points in set A comma B is n is equal to exponential minus lambda B minus A into lambda B minus A to power n divided by n factorial. This power n is in both lambda B minus A. And the second property is, if number of points in any k disjoint sets, if we consider, then these are all random variable. Okay, so number of points in A1 and number of points in A2, they are independent of each other. Similarly, if you take 3 or 4 sets, disjoint sets, number of points in these sets are also independent. So Poisson has this very nice property that two disjoint sets are independent of each other. The number of points in these sets are independent, and then the distribution is also independent. So I can extend it for a journal case with not a uniform density, but any non-constant density. So in that case, I will say the point process is a Poisson point process with expectation measure capital lambda if number of points in any set A is Poisson distributed with mean lambda of A. So this mean is anyway fixed, lambda of A, because of the expectation measure definition, but it's also a Poisson distributed. And also the second condition is same, number of points in any set is and any k disjoint sets are independent. So again, let me say what is the Poisson distribution. It means probability of that there are n points in A. In other words, I will write it phi A is equal to n is equal to exponential minus lambda A into lambda A to the power n divided by n factorial. This lambda A is a single number, is the mean number of points in A. And if I know the density, then lambda A should be equal to integration of lambda x dx over the set A. If this is uniform, then lambda A is equal to just small lambda density into the size of A. And this is true for one-dimensional or even higher dimensional, because expectation measure can be defined for any dimensional space. Now I will introduce one more point process, which is known as binomial point process. So a binomial point process
has two parameters, lambda and w. Sorry, n and w. A binomial point process with this parameter, it is a point process consisting of n points, where each point is located in the set W independently of other points. Okay, so each point is independent, and each point is located inside W somewhere, and the distribution again depends on the density of a binary point process, and it's also a parameter of this BPP. Here remember that number of points in the complete set W is fixed to be n. In a Poisson point process, number of points in any set is a Poisson random variable, which is not fixed, but in binomial it is fixed. So let us see a special case, which is a uniform binomial point process. So in this case, what uniformity means that the point rest is same, there are n points, the points are independent, and the only thing here would be that points is randomly located in W, and that random location is uniform. It has a same probability, to be anywhere in the set W. So know that what does uniform means? It means that if I take a half of the set and ask what is the probability the point would be in this half, that probability should be half. If I take 1/4 of the set, the probability should be 1/4. So basically, a uniformity generally means that the probability that a point will fall in that small subset of W should be proportional to the area or the size of that subset. So this means probability that ith point X lies in A is equal to size of A divided by size of W. Right? And size of W is in the denominator is to make it to normalize this. So if I put A equal to W, I will get 1. So probability that X would be in W is just size of W divided by size of W, which is 1. So this tells that if you take a larger set, the probability would be larger. If you take a double set, the probability should be double. And if you take two small sets of the same size, then the probability would be same. Right? Let's take a set A and B of the both same size. Then the probability that the point would be in A is equal to probability that the point would be in B. And that is where this uniformity comes. So now if there are n points and each of them is independent. So if someone asks you, if I fix set A, what is the probability that there are k points? Okay, so there are n points. Each point can be in A with p probability and will not be in A with 1 minus p probability. It's a Bernoulli random variable with parameter p. 1 means it is in A and 0 means it is not in A. And to get the number of points in the set A, I have to add all those points which are falling in A. So if I represent it by a Bernoulli random variable, so xi for point xi, first point x1, let us define indicator n1, and if n1 is 1, if the point is in A. Similarly, for the second point, it is n2. So if I add all those ni's, I will get a total number of points in A. And each ni is a Bernoulli random variable with parameter p. So summation of these ni would be a binomial random variable. Okay, you can also see it as a success event. A point falls in A is a success, and if there are n experiments, what is the total number of success? That is distributed as a binomial distribution. So the point of that probability that there are k points in set A is equal to n choose k, p to power k, 1 minus p to power n minus k. So pk means There are k points inside A, and there are n minus k points outside A, and there is n choose k ways you can select this point out of n. So this was true when A was inside W, right? What if A is outside W? I mean, A does not lie entirely inside W. Let's take this case. This is my W, and I am taking a set A. In that case, you can know that since the point can only be in W, this part of A does not mean anything. So probability that a point will fall in A is proportional to this intersection area, which is A intersection W. So probability that X belongs to A is probability of, size of A intersection W divided by the size of W. Now I want to show a very interesting result. I have talked about two-point process, Poisson point process and binomial point process. I would like to show that they are related to each other in a very simple manner. So let's start with a Poisson point process. I will take a uniform one with density lambda, and let us fix a set W and a small subset inside W A. So this is W, this is A, and this is W minus A, which is outside A. So number of points in set W is Poisson, number of points in set A is Poisson, number of points in W by A is also Poisson. And I also know that since A and W minus A are disjoint, number of points in this set are independent. So given that in a set W, number of points are n, right? Normally it is a Poisson distribution, but I would like to calculate that if I condition on the total number of points falling in W, what will be the distribution of A and W minus A? Okay, so just to repeat, W number of points in W are Poisson distributed, but here I am conditioning on it. I am conditioning that total number of points in W are fixed n. Then what is the distribution of A and W by A? Okay, so this means out of all point configuration, I am only taking those points configuration where total number of points in W are n, and I'm redefining my probability measure to find out the probability that out of these many point configuration, what is the chance that the point, what is the point probability that the number of points in A is k. Okay, so mathematically what I'm saying is, what is the probability that number of points in A is k, condition on number of point in W is n. So let us compute this. So here I am going to use two main results, basically by the definition of Poisson point process. First is, for any set A, it is a Poisson distribution. Total number of points in that set is follows this particular distribution, and disjoint sets are independent. So let us see this object. Probability phi A is equal to k given phi B is equal to n. Again recall, phi A is number of points in A and phi W is number of points in W. So this is equal to that phi A is k and phi W is n divided by phi W is n. So I say that total number of points in W are n and A in k. This is the same as saying that total number of points in A is k and total number of points in W minus A is n minus k. Because if these two are true, then total number of points in W is n, and there is no other way. So they are equivalent. But if I denote this way, what I get is, because these two are independent, I should be able to compute its probability distribution by just saying that this is equal to probability of phi equal to k into probability of phi W minus A is n minus k because of the independence. So now what is the probability of phi equal to k? It is this one. And probability of phi w minus a is n minus k is this one. And then also, this is also Poisson distribution, so I'll have this. Let us further solve this. What I do here is, I'll take this to collect this term together to get this one. I collect this term to here, and then I have this. And then I notice that if I add lambda a and lambda w minus a, I should get lambda w. By total mean number of points in A and the mean number of point in w minus a should give you mean number of points in w, because w is made from a union w minus a, and these two are disjoint. Okay, so expectation measure is a measure, right? And recall the measure properties. The measure has this nice property that if mu is a measure, then mu of a and mu of b is equal to mu of a union b if a and b are disjoint. Okay, so because expectation measure is a measure, it follows this additivity property. Because of this disjoint, you would say. Okay, and even if you do not apply this measure result, it is very easy to see that because W is partitioned into these two sets, total number of points in this set plus total number of points in this set should be equal to the number of points in the set W. So now I can add this. This will be lambda W, which will cancel from this. I will break this lambda W into two parts. One will go to the power lambda a to the power k, and second rest part will go to here. Okay, and then this will become n factorial upon k factorial and minus k factorial. Okay. So this is k factorial. This is also k factorial, k factorial, k factorial. So now if we look at this one, and again lambda w minus a I can write as lambda w minus lambda a. So this will becomes 1 minus lambda a upon lambda w. Now if you look at this is nothing but the binomial distribution. Okay. Total number of points in K, the unconditional, where there is no conditioning, total number of points in set A is K, has this property. Okay, so it may be a little bit hard to see because I have taken non-uniform case. So let's see this, how this will be equal to the binomial point process. Let us assume the PPP is uniform. So lambda A is just lambda into size of A. Lambda W is just lambda into size of W. So now if I put them back, this lambda cancels and I get this one. Okay, so this is P, the probability that set point will be in A. And this is 1 minus p. So this probability is the same distribution as shown in the binomial point process, which indicates that if I condition on the total number of points in a set W to be fixed in a PPP, then that distribution would look like a binomial point process. Okay, so it can be shown that PPP in a set W conditioned on the fact number of points in W is constant n, it behaves like a binomial point process with parameter W and n. So you can use these results on each other. So if I somehow fix number of points in this condition on that, then I can use results which are given for binomial point process. Okay, and yes. Now discuss two important facts which are related. One is I'm going to use some terminology in this course. So let us get familiar with that. One is a Dirac measure. A Dirac measure is the measure of the following format. Okay, so for any set B, its value is indicator that X belongs to B, and this X is deterministic. Okay, so it's just one coordinate. So for every coordinate, you will get a very different direct measure, and it just says it is concentrated on one point. So if any set contains that point X, its measure would be 1, otherwise it will be 0. Atomic measure is summation of some Dirac measures. It is in the following format. So it is concentrated on some points, that if B contains those points, then it will get some non-zero value. And if B does not contain any of this predefined point, then this measure is 0. So it means that if you're just making one set, if it contains these points, it will get some non-zero value. So it is concentrated on some points, and for rest location, it will give you a 0 value, no matter how big, no matter how you take any set of a very large Lebesgue measure. So counting measure is also atomic measure, because this is how a counting measure is defined. And third thing is diffuse measure, right? Diffuse measure is different because it will assign 0 measure to any set of 0 Lebesgue measure. Okay, so if you have, what are the sets of 0 Lebesgue measures? So any set with singleton points. It's in this case, if you have, just take a singleton element which has x, then the measure would be 1. But here it is saying that if you take any such singleton point set, the measure would be 0. So you have to take a set of non-zero Lebesgue measure to get a non-zero value. That is a diffuse measure. So now there are different types of point processes. One is simple point process, which means there can be only one point at each location. Probability that you get 2 points at any location would be 0. And most of the point processes we are going to study in this course are simple point process. Second is locally finite point process, which means if I take a set of fixed size or finite size, number of points falling in the set should also be finite. Okay, so in short, number of points in bounded sets are finite. You cannot have infinite number of points in a finite set. Of course, if you take a very large set of infinite size, like the complete RD space, then number of points in that space can be infinite. But if I take a finite subset, number of points should be finite. Then there is the atomic PP. Atomic PP means it is made from atoms. So the atom means there are some locations, coordinates, and the probability that you will see points of those location is non-zero. Okay, this means with non-zero probability, you will always see points at those locations, and such locations are known as atoms. The example you have seen in the past where we had a point process which has two realization. One there was 2 points and one there was 3 points. So if you take any realization and you focus on one point, there is a non-zero probability that a point would be there. Okay, so atomic PP is a point process which has at least one such atom. Okay, so it may have location with non-zero probability to be being included, but it has at least one point where you would see a point with non-zero probability. Okay, and if you compute the expectation measure of this point process, you will also get a atomic measure as the expectation measure. Because the mean number of points, so expectation measure is what? The mean number of points in any set. And because the point is included, the mean number of points at that set is some non-zero values. Diffuse point process is one which does not have any atoms. Its expectation measure is diffuse. It means if you take a set which has singleton elements or has zero Lebesgue measure, mean number of points in that set should be 0. Then there is a discrete point process which is purely atomic. It only consists of those atoms, and it may not contain any point, any location which has diffuse measure. Second thing I would like to cover is what is independence over sets and independence over points mean. Okay, there are two different things. One is you have point independence. It means each point is independent. And second is the set independence or the area independent, that if you take two different disjoint areas, those are independent. So first thing, you can take this point independence. It means the distribution of A is where it is located is different, is independent than the distribution of point B. Okay, so if point A is in this set, that does not change the distribution of point B. That we call as point independence. And the area independence means if I take these two disjoint sets W1 and W2, what is going on in this set is independent of what is going on in this set. If we have 5 points, that does not change the distribution of W2. Okay, so the first property, the points are independent. That is in both binomial point process and Poisson point process. In Poisson point process also, if you have all the points are independently located, in a binomial point process also, by definition, the points are independently located. But the area independence only exists in Poisson. That if you take two disjoint sets, number of points in this set and their location is independent of number of points in this set and their location. In binomial, that cannot be the case, because if this is set W, and if you take W1 and W2, if there are 2 points here, then this should have n minus 2 points, because total number of points should be n. So this set distribution does change or affect the distribution in the other sets. So binomial point process does not have area independence.